Okay, Assalamualaikum warahmatullahi wabarakatuh. Alright, for today's lessons, actually on the next topic, which is the chapter number 2, topic number 1, which is analysis of section. Okay, for this topic, we are going to divide into two parts. Okay, so for this lecture will be the first part of analysis of section. This topic is aligned with CO1 PO2, which is you need to analyze the reinforced concrete and steel section. Okay, for the learning outcome, at the end, you should be able to understand the relationship between the stress and strain in concrete. And then we need to understand the failure criteria under reinforced, balance, and over-reinforced design. And you need to understand the application of stress block in the design of beam. And then we are going to apply stress block analysis to determine the ultimate moment of resistance in reinforced concrete beam. So basically, we are going to look into how do we get the formula in design. Okay, so this is the beam behavior in bending. So this one is just basic concepts of reinforced concrete. When we apply load, the top surface will be in compression, then the bottom surface will be in tension. Since concrete is poor in tension, so there's going to be cracking at the bottom surface. So we add steel reinforcement to enhance the strength of concrete in tension. Alright, so for there are three types of failure modes that could occur in design. The first one is under reinforced, balance, and also over reinforced. Okay, so what is under reinforced means? For under reinforced, it means that the area of steel reinforcement that we provide to cater for the tension is relatively very small as compared to the area of concrete. So it means that the steel will reach its yield strength or steel will fail first as compared to the concrete. So steel, when we apply load, then it will have a small crack at the bottom of the our member, for example beam. Okay, so the next one is the balance. Balance means the steel will reach its yield strength at the same time as concrete. So it means that the failure of concrete and the failure of steel is at the same time. So we can predict how much is the maximum load that we can apply. So that is why this is what we call as ideal design. So we can predict the maximum load. And another one is over-reinforced. Over-reinforced is strictly not allowed because it means that the concrete will reach the maximum strength earlier than steel. So since we provide a lot of steel inside our members, so the concrete will reach its maximum strength earlier than steel, and the failure of the concrete in compression. This failure will occur without warning or sudden failure. So that's why we need to avoid this kind of design. So in design we cannot put very little reinforcement and cannot very much reinforcement. So it must be in balance so that we can predict the maximum strength of the members. Okay, so in stress and strain of a section, this is the what we call as stress block is the development of stress block when the concrete behave in bending. So, at the beginning, concrete is considered as elastic, so the stress and the strain will be in linear form. Okay, the shape is triangular shape. So this one is the compression stress in concrete. Okay, so and then when the concrete reaches its maximum yield strength, it will react like a plastic. So that is why the strain is constant, but the stress is increases. So that's why we get these rectangular parabolic stress blocks. And to simplify these rectangular parabolic stress blocks for the design, so we simplify this stress block into a rectangular stress block. So we are going to use this stress block to compute the design formula. Okay, so this is the three phase of the block, stress block, which is triangle stress block, parabolic, rectangular, and the simplified one. Okay, so before we begin, so let's look into the type of beams that we have. So we have rectangular beam and also flange beam. So first we are going to look into rectangular beam. So it means the shape of the beam is rectangular. For rectangular beam, we are going to have single reinforced or double reinforced. Okay, so two type of rectangular section, which is single reinforced and also double reinforced. Single reinforced means we have only tension reinforcement at the bottom. So here is the tension reinforcement. However, we need to put reinforcement at the top as what we call as hanger bar, so that we can produce a cage-like arrangement. So since we are going to tie our link, so we need a reinforcement at the top. So this reinforcement is not carry any load. For double reinforced section, it consists both tension reinforcement and also compression reinforcement. Okay, so you have a top reinforcement and bottom reinforcement. So top reinforcement is compression reinforcement, bottom reinforcement is tension reinforcement. Okay, so this is the cage-like arrangement, which is we need to tie our link. So this is link, shear link. So we need to provide reinforcement at the bottom, at least 2, and also reinforcement at the top, at least 2. Okay, so that we can get this kind of arrangement for beam detailing. Okay, so we are going to move into the stress block. How do we draw a stress block for a rectangular section? So first we are going to look into the single reinforced rectangular section. For single reinforced rectangular section, so we have bottom reinforcement only. For example, this one we have 3 numbers of steel reinforcement. So here the size of the beam, so B times H, and the depth of the effective depth of the section. Effective depth is taken from the top surface to the center of tension reinforcement. So here is effective, the distance of effective depth. Okay, so then we draw a line of neutral axis. Neutral axis is taken about x value from the top of section. Okay, so you draw your neutral axis line, and then we draw the stress distribution in the concrete. So this one, the hash section is actually represent the stress, compression stress in the rectangular section. Okay, so the height of this compression section is about 0.8 from depth of neutral axis x. Okay, 0.8 x. Okay, so alright, so this one is represent the compression in the section, and the tension in the section is represented by the steel reinforcement. So we denote as the forces in tension and also forces in compression. So we have another one. So yeah, FCC means force concrete in compression. FST means force steel in tension. So we have two forces here in the stress blocks. Okay, so as we know, we only know the stress value. So how do we get the forces in the section? So if you can remind during solid, stress is equals to forces divided by area. So rearrange these formulas to get what is the force value in terms of stress. So the force value is equals to stress times area. Okay, so this is the stress times area. So you need to compute what is the FST value and what is the FCC value in terms of the strength of the concrete and steel. Okay, so we can formulate the equation by using the characteristic strength of the concrete. Since this concrete, when we design, we only consider the height of the concrete is using effective depth, which is we take from the top to the center of tension reinforcement. It means that all the concrete below this is ineffective. So it means that that is why our strength is about 85% of the total strength of the concrete. So we assume that the design strength of the concrete is only 85%. So to get the design strength, you need to divide with 1.5, which is the factor of safety for concrete. Okay, so that you get a design strength of the concrete. So design strength of the concrete is a stress. So how do you convert stress to forces? You need to multiply with area. So area here is the area of this section, which is the B value multiplied with the height. Height is 0.8x, so that you will get your FCC is equals to 0.567 FCKB times 0.8x. So 0.567 is when you divide 0.85 with 1.5, then you get 0.567. So this is the force in concrete in compression. Okay, so how about the force in steel in tension? So for steel, we need to consider the strength of the steel, which is Fyk divided by the factor of safety of the steel 1.15 times the area of steel. Area of steel here represent, since here we have three numbers of bars, so it means represent total area of steel. So you need to calculate total area. So you get your FST value equals to 0.87 Fyk ES. Okay. Alright, so here all the value is actually given since we know the size of the beam, we know what is reinforcement that we use. So the only value that is unknown is the depth of neutral axis. We cannot take the depth of neutral axis at the center of the section since the concrete below this section is ineffective. So you need to know what is exactly the value of neutral axis. Okay, so to calculate depth of neutral axis, we are using equilibrium equation. So here is the level arm, which is the distance between the FCC and FST. So since we know that the top surface to the FST is D value, and here is the half of 0.8x, so you get Z value equals to D minus 0.8x divided by 2. Okay. Okay, so then we compute equation for our neutral axis using equilibrium equation, which means that the total force must be equals to 0. So as you can see here, FST is pointing to the left and this one is pointing to the right. So means the notation is different. So FST minus FCC will be equals to 0. And you can rearrange the equation. So you get FST is equals to FCC. So you substitute all the equation that we have. FCC equation and also FST equation here. Okay, so here since we have 0.567 and 0.8, you can multiply this one and you get 0.45 FCK B times X. So the unknown is actually the X value. So rearrange this formula to get the equation for neutral axis. So using this equation, then you get your neutral axis. Okay, so that is how we compute the stress block in rectangular section. And from the stress block, we are going to calculate what is the moment of resistance of this section. So moment of resistance is actually the maximum force this section can resist. So if we are using a 3 number of bars, so how much is the maximum load they can cater? So that is, then we are going to calculate moment. Moment is force times distance. So the force here is FCC forces and also FST force. Distance between these two forces is the Z value. Okay, so then you can compute your moment. So by taking moment about FCC or moment about FST, the moment of resistance of the section can be calculated as follows. So moment is equals to force times distance. The distance is Z value. So you can substitute the equation of FST and Z. So you get what is the moment of resistance of the section. Or you can take the moment about FST or moment about FCC. So if you take the moment about FST, then the moment is equals to FCC times Z. Okay, so these two equations, you get the same value of moment of resistance. So this equation will be used to determine the moment of resistance that can be resisted by the section with specific area of reinforcement. So here we already know number of bar that we are going to use, so we can predict what is the moment of resistance. Higher reinforcement will get higher capacity to resist moment. Higher capacity to resist moment means that higher load that the section can take. Okay. Okay, so just now we are mentioned about over reinforced. It means we need to avoid over reinforced section. So EC2 has limited the X value. The neutral axis should not be more than 0.45 D. Okay, so ultimate moment of resistance. So this means this is the maximum moment that can be applied to the section, regardless what number of reinforcement that you use. You need to substitute into the equation. So we go back to this equation. FST or FCC times Z. So you substitute into this equation. The X value is 0.45 D. So at the end, when you substitute this value, you get the maximum moment of resistance equals to 0.167 FCK BD squared. Okay, so the ultimate moment of resistance. Okay, so this one you substitute into this equation, then you get this equation. Okay, so 0.167 is the coefficient that what we call as the balance, so that we get a balance design. So that's why 0.167 is called K balance. Okay, so the limiting value for a single reinforced section is K balance equals to 0.167. So we can rearrange the equation. So you get K is equals to M divided by FCKBD squared. Okay, so this is the first equation that you are going to use when you start to design. Okay, so this is the first equation. It means that if the K value, if you calculate the K value, you get the moment value and you calculate K value and you get less than K balance, then it is single reinforced, tension reinforcement only. If you get your K value is greater than K balance, then you are going to get both tension reinforcement and compression reinforcement. It means that it's double reinforced. Okay, so based on the level arm equation, so rearrange the equation by substituting the M and K value. So M and K value is based on K equals to MBD squared FCK just now. So you will get your second equation. So this is the second equation that we are going to use for designing reinforced concrete. Okay, so and then the area of tension reinforcement. So based on this equation, okay, so you substitute this FST equation 0.87 FYKAS and Z here. rearrange so that you get the AS value. Okay, so this is the third equation that you are going to use in design. Since in design we don't know how much is the steel reinforcement that we are going to use, so we are going to use these three steps to get what is the area of reinforcement required. Okay, alright, so basically this is the end of the first part of this topic. So we are going to continue for the second part for the next lecture video. Alright, thank you very much.